I think we're live.
Okay, great. Thank you. And welcome everyone to this workshop, Exploring AI's Potential to Improve Chemical Safety, organized by our research project, Trace AI. Um, while we are so happy that there are very many people that have signed up for this workshop, and while we wait for more people to drop in, we would kind of ask you to scan this QR code and start with answering a few questions on Mentimeter so that we know a little bit about you. We will present and discuss that a little bit later. Yes. So, and of course, the information that we gather through the Mentimeter will be treated anonymously and only for during this workshop. So my name is Daniel Slunge. I am an environmental economist here at the University of Gothenburg, and I have the pleasure to share this session and herd the cats in this project. So just briefly
in the Q&A, you can now click on a link if you have a problem using the QR code, just for simplicity. Thank you.
Thank you, Eric. So can you press next slide, Eric? Thank you. So during the workshop today, we will briefly present this project and then delve into current challenges with information around chemical management and discuss how AI tools can be used to solve some of these challenges. AI in practice. You'll hear a short presentation from different members of this project. And then we will move into explaining a little bit about a survey that we are launching now to assess the demand for AI tools and also what tools are currently used, etc. That we would kind of ask you to fill in. And then we will also hopefully have time to discuss some Q&A questions before we end the first session. And we will, during the session here, you can chip in questions in the Q&A function, and we will try to respond to those simultaneously here during the workshop. And then we will have, after the first hour, we will have a 30-minute breakout session workshop where we can discuss things more in depth. And we will get back to that later, but we'll hope as many of you as possible stay on for that as well. So next slide, please. So you will say a few words about this, Eric, right?
I'm happy to do so. So we now have more than 70 out of 100 that have joined the Menti. So great, those of you who have. If anyone hasn't, you can go to menti.com and use that code, or the direct link in the Q&A, or scan the QR code to help us give us a sense of what comes to mind when you think about AI and chemical information. And what we see here is that complexity and efficiency, uncertainty, data are the biggest themes that pop up. But we also have a large range of things from possibilities to reliability concerns, automation potential, scary aspects, black box, and questions about safety and an unavoidable future. Yes, I think that will do for our first sort of just teaser brain kind of dump from you. So over to you again, Daniel.
So now I think most people have joined. We're 158 attendees. Great. So let me say a few words about this TRACE AI research project, which stands for Transparent and Accessible Information for a Chemically Safe Circular Economy. It's funded by the Swedish research agency Formas, and we explore how AI can help to improve access to reliable information about hazardous chemicals. With a kind of vision of a chemically safe circular economy. We are several partners in this interdisciplinary team. We have environmental toxicologists, life cycle analysis, environmental economics, and chemical policy, different experts from 3 universities, Stockholm, Chalmers, and Gothenburg. And also and part of Chalmers is also the Swedish Life Cycle Center. And we have the Swedish Center for Chemical Substitution at RISE, the Research Institute of Sweden. And then we have also ChemSec, which is an NGO working on chemical policy and substitution. And we hope we will provide some relevant content for you here with some challenges around chemical data and then the rapid development of AI tools. Yeah, I think we can then continue, Eric, with some of the Mentimeter questions and answers before we proceed with those aspects. Thank you.
Yes, it's very nice to see that we have such a spread of different categories of actors here joining us. 2 clear main categories. And that's the technical or scientific specialists and researchers, as well as the regulatory and compliance specialists. Still a few from more of the sustainability, environmental manager, etc., and policy analysts, as well as some others. So that's interesting to see. We're really interested in not only what the different actors or professional roles can contribute with and think differently in terms of this, but also what happens when we talk to each other in this between these different roles and professions, since we think that there might be some things that are kind of falling in between responsibilities here. So we have 2 questions more. I'm very happy that almost 50 have answered this question as well. And if you're still in the Menti, please go ahead and try to answer these couple of questions as well. So first one was then your main concern regarding the use of AI for chemical information. And here I will try to use AI actually to group your responses, see if I can manage to do that. So that's a little use of AI in the discussion of how AI can be used. So the themes that are emerging here are information gap. Sorry, there was a, I unfortunately clicked on the next. Okay, so main concerns: accuracy, biggest one; trustworthiness, also big; and then environmental effects, security responses. Yeah, and now if we instead go to opportunities and group those, there we have the information gaps and dealing with them: data integration, efficiency. Okay, I thought I would be able to scroll here. It's yeah, sorry for that. Just one final try. So again, information gaps, data integration, efficiency improvement, and literature search were some of the things here. Okay, so we will do this more proper analysis of your answers and provide that together with the recording and answers to Q&A questions that we have from this session afterwards that we email out to all of the registered participants. So you will have time to check that out if you're interested. Okay, and I'm handing over.
So, thank you. My name is Mikael Gustafsson, and I work as a researcher at the University of Gothenburg, primarily with different forms of modeling regarding chemicals and their flows in society, perhaps. And I'm going to talk briefly about challenges and opportunities in today's data landscape and give some form of quick overview of the chemical pollution impacts and spaces where we see potential for improvements. Because although we know that chemicals are an essential part of, let's call it a modern lifestyle, and we cannot really live without them, they also generate effects that are negative in the environment, for instance. So this is just an excerpt from the environmental agency, the European Environmental Agency, where they basically claim that the European Union project Solutions and Mars found that on average 20% of aquatic species in Europe are lost due to exposure to chemicals. And we also see similar problems when it comes to the human side of things. So there are, for instance, calculations on the burden of disease and cost of exposure to endocrine disrupting chemicals in the European Union, where there are estimates of annual costs of more than 160 billion euro, which actually translates to about 1.20% of the European GDP. And this publication is actually from 2016, and a more recent cost estimate for another type of exposure is the cost of PFAS pollution for our society, which is published by the European Commission. And here again, we see costs in the range of $40 billion per year in healthcare costs and remediation costs for PFAS in close to 4 billion per year. Now, any problems we have in the European Union are usually even larger in many low and middle income countries. So for instance, one of the things that we have problems with is material flows of, for example, e-waste that goes towards low and middle income countries. And the International Labour Organization estimates that as many as 16.5 million children globally are working in the industrial sector of recycling and scavenging these kind of materials. And you can kind of imagine what that does also to the local environment where this is happening. But anyways, the chemical market is increasing rather rapidly in parts of the world, and we see that the global sales is worth approximately 5,000 billion euro per year. But if we look at Europe specifically, we see something like this, the consumption of chemicals in Europe. And on the y-axis here, you have millions of tons that are used within Europe. And you see that this is quite stable. There are two small dips in the graph here of the total use, and that is the global financial crisis and when Great Britain leaves the European Union. And we also have an additional dip with COVID-19 striking us. And we anticipate this to simply go up again. So we have large amounts that are being used in society. And one thing to note here is that the orange bar actually shows you the proportion or the total tonnage that is actually hazardous in some way, shape, or form towards human health. And that is close to 80% of all the chemical consumption. Now, we don't only have large amounts being used, we also have a very great diversity in the chemicals that we use. And this graph simply shows you the number of chemicals that clever little chemists are figuring out every year how to create. And there are three things to notice from this graph. And the first one is that it's a very stable increase. So the rate of innovation is steadily increasing. And we also have this most latest number, which is that approximately 500,000 new chemicals can be synthesized per year. We have figured out how to do that. And the two dips that you see in this curve is World War I and World War II, which isn't really some form of solution to this kind of diversity problem that we're seeing. But a way to counteract this is for states to generate new regulations regarding chemicals. And what we see here is simply the growth in chemical regulation worldwide. And we see that in 2019, you were closing in on 25,000 regulations across the globe when it comes to chemicals. And that means that there is data and information generated within very many of those regulations. Now, we know also that there will be new regulations for sustainability coming up these years within the European Union. So for instance, we have the Circular Economy Act, which the proposal expected to arrive in 2026. And their circularity is seen as a foundation for competitiveness and strategic autonomy within the European Union. And the goal is, among other things, to double the European Union's circular material use to 24% by 2030. And that also means that they want to create a common European Union market for secondary raw materials, which again means that we need to keep track of the chemicals that are traveling within those raw materials. We also have the regulation on eco-design for sustainable products that is upcoming, and we hear some of the emphasis is on digital product passports, which will provide traceable product information throughout the entire life cycle of the product. And with that comes also requirements for information on substances of concern, which should be accessible to the consumer. And again, we believe that this will increase the number of data that is available to work with out there. So within both of these and other regulations, we see a great potential for reduced material losses, waste, and costs throughout the entire value chain if we can use this information in a smart way. Because in some sense, there is a lot of information out there. Now, this is just an excerpt where we look specifically at hazard and exposure data, simply because that's what we're most used to working with. And what we see is a number of data sources and the amounts of information that they maintain. But the problem here is, if you look in the top left corner, you see the US EPA Ecotox database, which has 50,000 scientific publications which have been tabled in there. But the thing is that data is very unevenly distributed. So you have a lot of information for very few chemicals. And I think that up to 20% of the data in there is based on heavy metals. And you see similar things for the exposure data, where again, we have very, very, very many measurements, but we would measure very, very few compounds over and over again. So we have a quite poor understanding of how it looks out there. However, we do believe that this data available out there will grow, both because new regulatory requirements are increasing the transparency. We have digitalization that is kind of going through society and making traceability feasible at a scale that it hasn't previously been. We also see a pressure from investors, consumers, and companies demanding greater supply chain transparency. And finally, this is kind of beyond the AI in itself, but we see that the adoption of artificial intelligence in society has created this drive to produce and allow access to data, because people now understand that data is valuable in itself and can be turned into knowledge. So if we look at that data landscape, different forms of data that we can anticipate to use in the future, we have the hazard and exposure data, but to protect the environment, for instance, you could allow data from biodiversity to be in there as well. We can take information from digital passports. We can perhaps play with how to do chemical regulation by doing agent-based methods with AI. We can think about using patent information and bring that in at an early stage, material flow data from different customs unions, product compositions in different forms, such as the one that is currently held by the Swedish Chemicals Agency could be in there as well. And we also think that socioeconomic data will play a role here, because as societies progress, you can see that more and more chemicals are being used. So despite all of this data being available, again, we're going back to the hazard and exposure just as an example here. The European Environmental Agency, again, estimate that there are approximately 100,000 chemicals on the European market, but only 500 of those have been extensively characterized for their hazard and exposure. And even if you count the 10,000 one where they say that it's fairly well, it still leaves you with approximately 90,000 chemicals on the European market, where we have very poor characterization of how problematic they are. So one way to solve that data gap that I kind of alluded to is to use AI in some way, shape, or form. And an AI is simply some form of black box model. And typical examples that you will have recognized or interacted with recently might be different forms of neural networks, which are used in large language models, such as ChatGPT, for instance, or Copilot, that a lot of you are interacting with. Now, these models are typically created without any initial assumptions, and they're defined by algorithms through their training. So basically, you're feeding in information over and over and over again, and you put that into that black box until the black box manages to match the input to the output, basically. Now, these are internally often very, very complex and hard or even impossible to fully understand for humans, and they have therefore a very low explainability, which is the term that we usually use. But they can have a very high performance and complex data, so you can merge data from very many different sources and kind of train the AI to see the connections between those data. But they are data hungry, and you need a lot of information in order to train them. Now, if you were to open one of these boxes, and look at a neural network, for instance, which is one of the typical building blocks for AI models, you would see something that looks like this. What you have is the large circles, which are nodes where information is stored, basically, and then it's passed through each and every one of these arrows in a learning kind of manner. And what you're doing when you do the training is basically to say how much weight you're putting into each one of these arrows that are passing along information. How important is that to the preceding node? And just to give you a sense of the scale that we're talking about here, ChatGPT-4, which is one of the more recent models, have 1.7 trillion parameters within it, and that parameters are those arrows that you see in the picture. So when we talk about AI, we also want to differentiate here between specialized and general AI. And the word AI model simply can refer to any model that has been trained on data. And the model has been allowed to find its own connections and its own correlations between the data that it has seen. However, that doesn't mean that the model in itself in any way, shape, or form think like a human being. It is statistically trained to learn patterns from large amount of data and uses those patterns to produce useful results. But the differentiation between specialized and general AI. So one example of a specialized AI would be typically a diagnostic tool, such as an image recognition tool that recognizes whether you have a picture of skin with cancer or skin without cancer. That is a specialized version of an AI tool. And these are typically task specific. That means that they're generally more accurate. And that also means that they become more trustworthy and have somewhat higher explainability and traceability and auditability, since you know what they have been trained on. The challenges with specialized AI models, though, on the other hand, is that they are data specific, they lack adaptability, and they need to be retrained depending on the setting that you want to use them in. In contrast, general AIs, such as the one that are used to train the chatbots that are sometimes called foundation models, are the task agnostic. They can solve problems not previously encountered. However, they do so in a complex way and have an even higher complexity than specialized AI models. They therefore have a very low explainability and a higher risk of hallucinations, which some of you alluded to as a problem before. And I think that that is mainly why, as far as I know at least, all AI methods that are currently used in critical decision making are based on specialized AI models. So what lies ahead for us, though, within this project and within society, perhaps? Well, we do expect data to grow, both from legal requirements on increased transparency, but also due to an increased understanding of the value of data. We also believe that AI models can incorporate many types of complex data, all the way from chemical to societal and judicial data, thus ensuring that better decisions can be taken. However, to ensure trust and higher performance, I think we need better specialized AI models that can then be integrated into general AI systems like chatbots, for instance. And we think that general AI models will be used extensively for summarizing, collecting, and overviewing data and models, but that they demand some kind of caution while being used. And with that, I would like to leave over to Styrbjörn to go over one specific AI model.
Thank you, Michael. So let's see, yes. So my name is Styrbjörn Kjell. I'm an industrial PhD student at a company called Nitec Group and at the Department of Mathematical Sciences at Chalmers University of Technology. And now we're going to focus on some sort of specific use cases for AI where we see large potential in this sort of consortium. So how this will work is that we will have 3 speakers, starting with myself, and we will have roughly 5 minutes per speaker here. So 15 minutes of interesting content coming up, basically. So I will first start by talking a bit about chemical property prediction. And then we will have Nina Melander from RISE, who will talk about chemical substitution and SSBD. And then we'll have Marlene Ågestrand from Stockholm University, who will talk about a specific AI agent that they have developed for risk assessment. So chemical property prediction. This is a very old field. It has a rich history. People have been working on it for a long time. And it concerns itself with taking a chemical molecular structure, inferring some sort of patterns from this structure and predict various types of chemical properties. This is, of course, important because we need to know various properties in order to make good decisions about various things. It could be regulatory decisions, simple safety sheets, risk assessments, candidate lists, whatnot. So these are sort of at the foundation of various types of decision making. And we have, of course, a lot of various chemical properties. I've only listed like a couple that came to mind. Boiling point, pKa, down to more complex types of properties like toxicity and biodegradation and so on. And historically, we've been able to do this through computational models. So it's not really necessary to do experiments to sort of derive these different properties. However, historically, these models that people have used have been quite poor in performance. And what we are currently seeing now is that AI is sort of switching these older models for new, better versions of themselves. So now we begin to get very high accuracy using these models. And just to sort of list the obvious here is that AI can then help us fill various data gaps for these properties. And thereby they can help us sort of be more proactive in our decision making for both existing chemicals and future chemicals. And as I mentioned, toxicity is one of those notoriously difficult properties to estimate. And as you may know, they have traditionally required animal exposure experiments where you would take your chemical, expose it to some animals, and then derive dose response curves, which you then use to sort of arrive at various toxicity metrics. And the nice thing with AI models is that we can bypass this entire sort of procedure by simply predicting directly from the structure these various toxicity metrics. And there are many tools that can do this out there, but quite few have sort of a good validation procedure in that you can trust what these tools are doing. However, one tool that we have developed is called Trident, where we at least claim that we do a rigid validation. And it's a specialized AI model, to connect back to what Michael talked about, which sole purpose is to predict chemical toxicity. So it does nothing else, no fancy chatbots or anything. Here we see it in use. So basically you can take any chemical structure, put it into this AI tool, and it will predict various forms of toxicity for you. This tool is a couple of years old now, so it then only supported what's called ecotoxicity, but now we are working on sort of the successor to this tool where we can also start to integrate human toxicity. And just to sort of delve a bit deeper into the concept of specialized versus generalistic AI models is that you could, in theory, do this type of prediction using a general model like ChatGPT as well. But you lose a bunch of guarantees when you do this. So when you have a specialized AI model like Trident here, for example, the training data is available. So we know all the data that was used to build this model. We have a publication with a thorough validation procedure. We provide error estimates. And in a way, this then becomes more traceable and auditable than its counterpart here, ChatGPT, where We don't know the training data. There is no validation of this specific task of predicting toxicity. There's no error estimates and so on. So this was a very sort of brief walkthrough from property prediction to toxicology. And here are some hot takes that I thought about. So basically what I can conclude is that from toxicology, from that perspective, this is sort of passing the tipping point now, where many of these developed AI models are accurate enough to start to fill and close these knowledge gaps that we have had before. And this is also true for a variety of other chemical properties. However, I want to also sort of point out that it's still difficult to implement these AI models in decision making. And here we have a lot of work to do to sort of build trust. But sort of as a first step towards this is this hot take here, which says that if we can control the data and we can control the model design, we can start to build trust around these systems. And if we can build trust, we can start to make more critical decisions using these tools. So now I will hand over to Nina, who will talk a bit more about some other examples of AI.
Thank you, Styrbjörn. So my name is Nina Melander and I work for the Swedish Center for Chemical Substitution at RISE. And what you will see here is a short overview of AI tools that have already been developed to address challenges related to the goal of kind of finding safe alternatives to hazardous chemicals or start to integrate safe and sustainable by design thinking into innovation. This is not in any way an exhaustive list. It's more a snapshot to illustrate what is emerging right now. And I would really encourage any participant, if you know of any other tools, to add examples in the chat if you have any knowledge or awareness. I think Vera will add a specific thread for that to keep some order in the Q&A. But to be clear, these tools have not been systematically evaluated by us. The aim is not really to recommend any of these tools or a specific solution, but to illustrate that AI will have an impact in this field in one way or another. So for example, if you start on the left, you could have one of the first questions on like, how do we design and make molecules, preferably be with like safer and more sustainable molecules in the first place. And these tools then represent a shift that are listed towards accelerating this design, make, test cycle at a molecular level. So there seems to be AI appearing that can propose new molecules, suggest synthesis routes, optimize reaction pathways for sustainability, predict impurities, and supposedly even connect to automated labs for reducing this trial error and shortening R&D cycles. And once a molecule exists and its kind of production route, one of the next challenges is, of course, how do we turn them into functional materials and formulations? And there seem to be some AI tools that support the prediction of material properties and optimization for performance. So instead of running like many experiments, AI can then run virtual experiments and learn from existing data and suggest optimal formulations. AI can also help with information management in various ways. And also, instead of manually searching literature, AI can scan publications and patents and databases to suggest viable substitutes much faster than previously. And also supporting matching then functionality and performance. So this can include things like solvent substitution or ingredient replacement, but also broader kind of material alternatives. There are also some interesting tools that start thinking about not just replacing a chemical with another. So you might think about new solutions or bio-based materials. So AI supporting discovery of bio-based ingredients. It could be identification of new material combinations, but also translation of biological strategies into design concepts called biomimicry, as example here by Ask Nature Chat. But there are also tools like MakerSite that are supporting more on a product design and lifecycle decisions. So supporting and making more holistic decision across the entire product lifecycle. So here, digital twins can help companies compare alternatives in product design and understand various trade-offs in the lifecycle and design more sustainable products from, adding a bill of material. maker side, as I understand it, also supports in chemical regulation and to some extent on generating data gaps for chemicals in the supply chain. And they do this by integrating both supply chain data, environmental impact, and regulatory data. But if you're also moving from design to kind of evaluating a more kind of strict sense of substitution or safe and sustainable by design, AI also supports in regulatory monitoring and scanning, as with 3Insight, but also extracting and interpreting toxicological data, conduct hazard and toxicity assessment. And there's seems to be one option that is also using an agentic workflow that conducts entire alternatives assessments that are very specialized and trained and suggests safer options. So AI seems to be able then faster, more scalable assessments of alternatives in various aspects. One more kind of strictly substitution tool in the more strict sense seems to be the IBM Safer Materials Advisor, which is an AI-based tool for screening chemicals in product and supply chains with a current focus on identifying PFAS. So the tool automates then the analysis of safety data sheets and other technical documentation to identify substances of concern and then maps them to regulatory frameworks, flags potential hazards, and also support the identification and evaluation of possible substitutes. So it conducts then these alternatives assessment to gather data on various hazard trade-offs and supports in new materials discovery. Another example for more focus on the toxicity and assessment space is Human Chemical, which is an AI platform for chemical hazard and risk assessment. They claim to be then using this very specialized AI agent that's been trained quite strictly, and they say that there is no hallucination in this case. So it uses scientific literature, regulatory databases, and predictive models then to generate these structured safety assessments. So the claims here, of course, that it conducts alternatives assessment and reduces the time to gather this data from 1 to 3 weeks to 15 minutes, as well as the redesign for safety and sustainability. So these are just some examples of tools that are emerging in this field. So I think we can say that AI will have some type of impact in our sphere of safer chemistry and chemical substitution, and will have a role, play a role as an enabler for safe and sustainable innovation. And with that, I would like to say thank you for me and hand over to Marlene.
Thank you. My name is Marlene Ångstrand, and I'm a researcher at Stockholm University working with risk assessment and regulation of chemicals. I will talk about two AI agents that we developed for risk assessment that aim to help risk assessors make use of available information from the scientific literature. And I've done this together with Anna Peronius. We have for many years developed manual tools for different processes in risk assessment, and now we've teamed up with Stefan Foss Hansen to transform and expand these tools to AI agents. The AI agents I will talk about address the step of screening and evaluation of data for regulatory purposes, but of course you can use them also for academic purposes as well. So we heard before about one of the main problems in chemical regulation is the lack of information, but another rather big problem is that it's the opposite, that we have too much information, and how do we find the information that we actually need for assessment. So we tried to address this by developing a tool that screens and categorizes peer-reviewed studies. This example is for 4,500 papers on micro and nanoplastics that the AI tool then categorized. And for example, the first row, you can see that it categorized 725 of the studies as into the category environmental effects and ecotoxicology, and then we can move forward and then select the ones that we want to have for risk assessment, because this tool provides a justification for why these substances were classified into this category. I provide two examples here of the justification that you can easily pick up. Okay, I want to look at the reprotoxic effects of this substance, and you can then find them easily. So this tool help risk assessors to decide which studies to move forward with, but also displays knowledge gaps within the field, and it does so super quickly. So far, there's one example. We have 7,000 papers that we've gone through in 4 hours, which is a huge difference compared to doing this manually. So that was a first step, and then you want to know, are these papers any good? Can I trust them? Can I use them for risk assessment? We have typically done this manually before, and we have tools for that, and we have now transferred them to AI agents. And this example here is for nano ecotoxicology studies. And I'm going to show you a short movie that's just displays how the tool is working. So it's you provide it with the paper you want to evaluate. In this case, it's going to evaluate 21 reliability and 13 relevance criteria. It provides some kind of score or some kind of overall idea for each criteria, and together with the reasoning that gives this transparent and structured way of assessing every studies. And there's also a possibility to have a dialogue with the tool, with the AI agent during the process, and see if everything is understood correctly. So this the question then is, the big question is, can we trust this? We saw this from the Mentimeter, that this is a big thing. Can we trust the AI tools? So what we did in this project was with the help of experts from and their evaluations from regulatory agencies in European Union and Canada, we compare this with the output from the AI agents to see, like, do they agree, where do they not agree, and how can we improve the AI agent? And overall, there was a very good overlap. It's very promising. There were some examples where the overlap wasn't as good as we hoped for, and then it helped by having like clarifying with the AI how to address certain type of data. And one example of that, it was those response curves that were difficult for the AI tool to fully understand. We saw also some significant differences depending on if you use free platforms or subscriptions, but also which kind of model you use. So it's better to use the deep research model instead of instant answers. But overall, oh, sorry. Did I? Okay, someone took control here. Well, overall, I just want to say that we see the value of AI and what it can bring to risk assessment, and we hope that our work can help speed up the process while also maintaining trustworthy assessments. And I just also want to say that we have publications in the process. Unfortunately, we are not as fast as the AI tools, so you will have to wait for them just a little bit longer. Handing over to Eric.
Or Vera will join
Vera,
us
sorry.
first, but then, yes.
Yes, so thank you, Marlene. My name is Vera, and I am a research assistant at Trace AI. And so we've now, in this previous section, talked about AI-based tools and a lot of different examples of what is being developed and used today. So what we would like to do now is to take a step back and ask, what are the actual needs and priorities, concerns across different stakeholder groups regarding the development and the use of AI-based tools for chemical information and assessment? To better understand the needs and perspectives of different actors, we have made a first mapping of seven broad stakeholder categories, as you can see here. And based off of the background information you gave in the Mentimeter, we know that we have representatives here from the regulatory sector and researchers and many more. And there may, of course, be additional groups or roles that are relevant, and this is part of what we want to learn and explore with you today and in the future. Because beyond researching how AI-based tools can be used for chemical information and assessment, Trace AI aims to build a broader forum for dialogue on this topic, and we hope that this can become a space where different stakeholders can share needs, experiences, concerns, and where we can create this joint exploration of how AI tools can be developed and used in both responsible and useful ways. So as a first step, we've created a set of surveys to collect more in-depth input from key stakeholders. And so the purpose of the survey is to identify these needs and practical constraints, opportunities and risks among stakeholders such as yourselves. And your input in this survey will help guide the project's research agenda and the continued development of AI-based tools. So what we've done is create tailored surveys for the 7 stakeholder groups that I showed on the previous slide. And this is so that the questions are as relevant as possible to your professional experience. So you can scan the QR code here on this slide. It will take you to a page with short descriptions of the 7 surveys, and then choose the survey that you, best matches the type of organization that you work for or the role that you have. We don't expect you to complete the survey right now during the workshop, but we would be very grateful if you could take some time to fill it in sometime this week. This survey is in English and it takes about 15 minutes, and we will also send out the links by email after the workshop. And your input is very valuable to us, both for shaping the project as well as explore how this future forum around AI and chemical information can be useful to many actors. And I will now hand over to Eric.
Yes. So thank you so much. I'm just going to continue where Vera left off, and just to highlight that we want to explore together with you multiple sort of coming together in different ways, the needs, interest, but also the barriers to using AI for chemical information in a safe, sound way. And our aim, as Vera said, is very much this kind of learning and co-learning of the possibilities and how to overcome the obstacles, etc. So this is just an illustration of that we will try to use a multimodal sort of data collection and form of stakeholder interactions, where we will use workshops, surveys, interviews, focus groups, literature review, etc. And also in terms of the interviews, in order to try to be able to both go deep and also go wide and to many, we will explore using AI interviewers to facilitate what simulates semi-structured interview, where you ask follow-up questions based on the answers you get. So in this way, we can sort of have more of explorative data collection that in other research fields has shown to be promising. So that's a part of what we will be doing here. And this will take place mostly during the autumn. In December, we will have an in-person workshop in Stockholm. And in the end part of the survey, there's a link to another sort of form where you can indicate your interest in joining that workshop. Unfortunately, we won't be able to invite everyone, but we're happy to try to invite a few. And then other ways of staying in contact is to follow us on our LinkedIn page. So I will now hand over to Daniel to say some words before we wrap up this main part of the session, and then we will have the more interactive part after that. But Daniel?
Yeah, thanks, Eric, and thanks everyone for making all these succinct presentations. We actually have a few minutes here where we can take some of the Q&A or questions raised in and comments in the chat. But yeah, maybe we should start there. There's been a bit of a dense information coming here. Fortunately, we will share presentations in a PDF, and we will also post the seminar online if you want to view it again, or share it with a colleague or something like that. I saw one question, if we start here, by Albert Anguera Sempere, who said, with regard to human chemical statement, any generative AI model will hallucinate due to the constraints during training. And this raises then this question of trust. And can we really trust these models in regulatory decision making, etc.? Styrbjörn, you said we would need to work a lot on this, if I understood you right. But would you like to comment this?
Yeah, sure. I can try to comment it at least. So yeah, I think this is one of the fields that we need a lot of more research in. One can say in general, as well as a complement to this question, actually, is that there's quite little research being made into how we can sort of encourage both our society in general, but also regulatory decision makers to adopt these AI tools. That's almost a research field in itself. But in general, I mean, one can say that we need to control the data that's used to build these models, because if we don't know this data that the model is built upon, it's very hard to build the trust that is required for us to use these tools in future use cases, basically. And for a lot of sort of these general AI tools, which we have seen presented here today, like chatbots and agents and so on, I mean, they are very good sort of as an interaction tool between a human user and some sort of machine or database or whatnot. But they by themselves are not that good. So we can't really trust that their training has made them robust enough to make critical decisions. Rather, we try to sort of enforce this by instead adding specialized AI models that the general models can then use to sort of make decisions based upon. So we basically give out specific tasks to various models or databases where this general AI model simply acts as an interface between these highly specific models or databases and a human user. That's, I think, where we will see sort of the future be heading, not to use these chatbots directly to make decisions, basically. I don't know if that's good enough answer to the question, but it's at least somewhat.
Thank you, Styrbjörn. We'll take one more, and I see someone is raising his hand here, but I don't think we can unmute participants
we
here.
have
So please.
we have allowed him to unmute, so I think Thomas can unmute and ask.
Okay, please ask your question then, Thomas.
Okay, thank you. Yeah, thank you for great presentations. I have two questions that are somewhat connected. One is, in order to design many policy instruments, we need to compare the toxicity or hazardness of different chemicals. And we often refer this as a weighting problem. And I'm wondering if you think that these AI, basically, I'm guess I'm turning to Styrbjörn with this question. If you think that you can create an index that would be sufficiently certain to be used in this kind of a way, and I'm imagining that there would be conflict, and that maybe industry and NGOs and consumer groups could have different opinions. And some of the other so my other question is, in the sort of safe by design kind of mode, if you start integrating those people who are critical of chemicals and into the safe by design, then they become rather co-opted and part of the system. Will it not be difficult to maintain a role as an independent critic as well?
Thank you, Thomas. Styrbjörn, do you want to go on that one?
I was going to say that maybe Nina can start and talk about the SSBD so we get another perspective into the discussion.
I'm not sure I 100% understood the question, so I think that was my challenge.
Okay.
In regards of the safe and sustainable by design.
Yes. So suppose you invite people in who are somewhat critical of the chemical, of a particular group of chemicals, and you invite them in to a sort of safe by design process. Then they become co-opted. They become co-responsible. You suggest somewhat less dangerous chemicals, but then it becomes rather hard for you to criticize them because you have been part of the of suggesting them.
Okay, so you mean like a third party that helps in assessments?
Yes.
Yeah, so I think in regards to safe and sustainable by design in general, there is this discussion where, for example, companies might need third party support when it comes to evaluations. And I think it's important that the third party is a transparent provider of data, where you show kind of the data that you have been used and what are the risks and opportunities with various molecules, because there can be many trade-offs. It could be many trade-offs between potential hazards. Could be uncertainty in data, which is quite common in innovation, and a lot of innovation has adapted to managing uncertainty in data. And I think this is one aspect, and you could have trade-offs in sustainability. And I think it's probably important that the support provider provides data, but the decision and the responsibility of the decision, I think, has always been on the company or the developers. And I think that's like a very important role separation. And that's just some initial thoughts on that question.
Thank you, Nina. So we are approaching the end here. I would like to thank you all again for attending. This is really a fast-moving area, so this is somewhat of a learning process, which we very much would like to do together with stakeholders of different characteristics, etc. So it would be really great if you would like to fill in the survey. Nina or Vera, you posted links also here in the Q&A. So please do, and we will also get back with further events, etc. In relation to this topic, and we hope you will join us there.